So the next circuit is this simple parallel circuit with the 220 ohm resistor and 330 ohm resistor in parallel with each other. And we'll go through the same sort of problem solving or circuit analysis as we did with the series circuit. So we first of all calculate the total circuit resistance, and we use this parallel combination expression, which I've already written here. RT equals R1 times R2 over R1 plus R2 for parallel combinations. And you can do this with as many as you want, although the expression won't quite be the same. This expression is specifically for two resistors in parallel. For three resistors, it becomes a bit more complex. We add in the numbers and we get a total circuit resistance of 132 ohms. So this basically means that this parallel combination is equivalent. It is, if I just do a purple box here, it is equivalent to a 132 ohm resistor. So now that we have the total circuit resistance and we already know that 5 volts is the total circuit voltage, we can use Ohm's law to calculate the total circuit current. And we plug in the numbers and we get a value of 0.038 amps. So being that we now know all these values, we have to accept the fact that the current will split at the parallel junction. So Kirchhoff's first law says that at a junction, if I have I1, in one path I have I2, and in another path I have I3. But I2 plus I3 equals I1. Now I2 and I3, their values or how their magnitudes depend on the resistances in the respective branches that they are going to. So most of the current will go in the branch with the least resistance. So the branch with the least resistance will take more of the share of current. The branch with the most resistance will take the least share of the total current. And without getting too deep into the mathematics, we can just use simply ratios. But it will be a reversal. So if we understand that 220 ohms is only 40% of the total resistance, then 60% of the current will go there. And if we understand that 330 ohms is only 60% of by the way, the total resistance of them together, not the total circuit resistance. So if 330 ohms makes 60% of their combined resistances, then it will only take 40% of the current. And I already predicted that we should see the same voltage across each resistor. So 5 volts comes in there. Now this current I2 still has 5 volts in it. And this current I3 still has 5 volts in it, because nothing has been used up even until they get to the junction. So even if more current goes in there and less current goes in there, each electron within that current still has the same energy per unit charge. So 5 volts has not changed until it gets lost on the resistors. So these two voltmeters would read about 5 volts each, and we can calculate it as well. So 40% of 0.038. So 0.038 multiplied by 0.4. The current going into this branch is going to be 0.0152 amps, and the current going into that branch is going to be 0.0228. And I've made a slight mistake, so I need to do that. So The current going into the branch with the least amount of resistance is 0.0228. The current going into the branch with the most resistance is going to be 0.015. And if we calculate the voltage, so V equals IR, so V equals 0.0152 multiplied by 330, the voltage in the branch with the resistor that has 330 ohms is going to have a total voltage dropped of about 5. So that's going to be 5.016 volts. And on this side, V equals IR, V equals 0.0228 times 220, and V should also be about 5. You can test this out on the calculator. Times 220, and it's the same exact voltage. Okay, so it's unsurprising that using Ohm's law with the respective currents will yield 5 volts each, because at a junction you split the current but you do not split the voltage. Remember what I said, voltage only varies in series, it does not vary in parallel, but current varies in parallel but never varies in series. So let's make a circuit and see how this actually looks with a real circuit. So the next circuit basically has the 220 ohm resistor and 330 ohm resistor in parallel with each other. So I've got power coming in on this side, and I've used 2 extra small solderless wires to recreate the parallel circuit more like what we drew earlier on. So the current splits off at the junction there. Some current goes into there, some of it goes into there, depending on their resistances. And the current then comes back together at that junction and then goes to ground. Okay, so in the theory, we calculated that the total circuit current should be about 0.038 amps. I hope this will be easier to measure on this multimeter. I mean, it is a cheap multimeter, and current is, it's not that hard to measure if you have a good multimeter, but I don't think this is a very powerful multimeter. It just does what it says. It tries its best. Then we also predicted that there will be 5 volts lost across each resistor, irrespective of the fact that they're in parallel. Irrespective of the current that each of them get, it will still be 5 volts lost, because even though you split up the current, you haven't used any energy yet until you get to an actual component. So 1 electron can go in there, 1,000,000 electrons can go in there. Each of those 1,000,000 electrons will still have 5 volts each. That 1 electron will still have 5 volts. Okay, so either way, 5 volts is going to be lost. Okay, 5 volts is voltage is a ratio. It's the amount of energy divided by the amount of charge. So if you lower the amount of charge passing, you lower the energy, but it's in proportion. So you're going to get 5 volts either way. So let's switch this circuit on and let's measure. So set this to measure DC voltage. So this is the 200 ohm resistor, I think. Doesn't really matter. We should see about 5 volts on both of them. Okay. So I'll just place that there. Place that there. So 4.88 volts. Why are we losing a bit of voltage? Well, because this is an imperfect circuit. So the wires that